My name is Michael Tost from Montana Universität Leoben, and I'm together with my colleague Lorena Munoz will be the chairs of this session here today. I'm just asking Farnaud from the World Resources Forum to please start sharing her screen so that we have the slides here as well. Hopefully you are where you want to be. You are in session 1B, which is primary resources, critical raw materials. And I guess without further ado, I just you wanna go to the next slide, please. Just very quickly talk about the session format and the voting procedures. So we would ask you to please, if you ask or have questions, use the chat here in Zoom, but also use the chat in the forum.
On the WOVA platform, sorry.
On the WOVA platform, exactly, as well. So Lorena will help me with that and check the WOVA discussion as well. But if you have any questions to our presenters, then please use both those chats. The format is very simple. We'll have 5-minute presentations from each of our speakers. You can ask your questions, as I've already mentioned, in the chats. And then after the 5-minute presentations, we'll have time for discussion and for presenting your questions to the speakers. At the very end, the last couple of minutes, we'll do a voting. We'll have a voting procedure, to which we'll get back to. But we'd ask you about who you thought gave the best presentation, who presented the most interesting research, and where to go from here as well. And then on Thursday, at the end of the overall World Resources Forum conference, the most voted for presenter will get an award at the closing ceremony. So I guess the stakes are high for our speakers, for our participants. And without further ado, Farnaud, if you want to go to the next slide, please. I want to introduce our first speaker, Dr. Ajay Patil, who is a researcher, scientist, and PSI founder fellow at the Paul Scherrer Institute in Switzerland. So Ajay, the floor is yours.
Oh, thanks, Chairs. Can you see my screen? Yeah. So thanks again to organizers for giving us a floor to present our result, and also to Chairs for kind introduction. So the today's topic which I am going to present is a circular economy of critical rare earth resources, technical and economic challenges. We as a solid waste treatment group with joint affiliation at Paul Scherrer Institute and Swiss Federal Institute of Technology at Lausanne in Switzerland are mostly engaged in the activities in which we try to exploit waste as a resource. And our aim is to recover materials, to substitute the fossil fuels, and minimize the dissipation of valuable materials or toxic ingredients in environment. My own research interests are mainly lying in recovery of materials, mostly the rare earths. So as most of us are aware that rare earths are a group of 17 metals, which are essential ingredients of almost all the modern electronics and technologies, right from cell phone up to satellite, and everything in between needs these raw materials. And their astonishing optoelectronic properties made it possible that we have a clean energy, e-mobility, and the smart devices accessible to all of us. Of course, their ever-increasing use is giving the problem of e-waste, which is at the moment the largest growing municipal solid waste fraction, with astonishing growth of 10% per year. This also gives then us the opportunity to use it as a secondary resource for these critical raw materials. And it has a potential opportunity because it is an increasing feed. As I mentioned, 10% growth per year in the feed. It is a need that we must develop sustainable waste management practices. And what could be better than implementing circular economy? Of course, it will also help us to get positive environmental impact, because the amount of material we can recycle out of e-waste, we will avoid mining that from the earth, and then the associated environmental impact. And of course, no balance problem. That means we recycle the material which are mostly asked for, and won't dump our markets and the landscape with unwanted material. Of course, as a saying that opportunities lies in the middle of difficulties, there are also challenges to exploit this opportunity as well. The challenges are like that there is a technological lag, because mostly the technologies are there for the mining industry. It's a complex nature of feedstock as a municipal solid waste, and it requires complex value chains to access. Most of the technologies and approaches struggle with output qualities and hence the economic viability. However, at Paul Scherrer Institute, we took up the task of technology development with the intention of implementation. So our developed technology can handle complexity of different e-waste streams, and pre-concentration of dilute metal content, so that our steady state process can focus on highest possible qualities, and which will eventually make the economics of recycling positive. Our current focus is lamp fluorescent powders and magnets, which are giving us access to at least 6 metals, rare earth. And in future, we will try to access the batteries and catalysts, as well as we will try to translate our technology to mining tailing to recover maximum value of rare earth byproducts. So what is our model process about, which is being implemented by our spin-off company Remretech? That we recycle the material after the feed intake with thermomechanical processes such as shredding, pyrolysis, and segregation. We digest the material so that we could place selective solution chemistry with it with liquid-liquid extraction. Finally, after high purity analytics and impurity profiling, we are in position to develop more than 99% pure metal product, which are then similar to what we get from mines, and they could be part of our front-end high-tech manufacturing. We could use our energy or mobility or high-tech gadgets or smart gadgets by using this raw material. And again, end of use, they become part of the sustainable waste management system and come back to our circular economy supply chain. In this way, we try to push the boundaries of the circular economy of rare earth value chain. So to conclude, we have successfully developed the processes to achieve more than 99% rare earth raw materials from lamps and magnet e-waste by using the hydrometallurgical approach, which has applicability to other e-waste forms as well after necessary modification, and it could be easily scaled up and implemented. Of course, so far we found that there are no operational and economic constraints, and this technology we will implement in terms of our spin-off company Remretech. Finally, I would like to take this opportunity to thank our financial supporters like Swiss Federal Office of Environment and EU EIT raw materials on EU level, and as well as our entrepreneurial financing supporters. Also, this work would have not been possible without the efforts of my team. I am representing this all of you for your attention. I would be happy to take some questions if it is possible after in discussion round.
As Michael indicates previously, we will having all the presentations. We will be saving your questions to the end. The question can be made through Zoom or through WOBA, and we will be saving it to have a last discussion. Right now, we will have Dr. Nora Bartolomé with her work entitled Critical, I couldn't go through it, Farnaud. critical metals from Schroeder's light fraction in end of life vehicles. Nora Bartolomé is an environmental chemist working on the field of sustainable solid waste management and circular economy at Empa in Switzerland. Thank you very much. The floor is yours, Nora. You have 5 minutes. You are silenced.
Good afternoon, everyone, and thank you for attending this talk about critical metals from Schroeder life fraction in end-of-life vehicles. Currently, one of the biggest growing waste is end-of-life vehicles, with a total of approximately 6 million in the 27 European Union countries in 2018. Vehicles are an extremely complex engineered product, consisting of many different components and materials, including, as you can see in the image, many critical metals. So for instance, we can find neodymium in the permanent magnets or indium in these plates. In the following flow chart, you can see that once vehicles reach their end of life, part of them are exported, then the rest are first depolluted and then partly dismantled from those parts that can be well sold in the market, such as for catalytic converters. After that, the end-of-life vehicle hulks are treated in shredders to separate mainly base metals, such as steel and aluminum, and precious metals from other materials. The rest belongs to the shredder life fraction, or SLF, and currently this fraction is incinerated and deposited in the landfill. The shredder life fraction is a very interesting, but at the same time very complex matrix that consists on approximately 20% of the end-of-life vehicle. It contains an extremely heterogeneous mixture of plastic, textile, rubber, wood, glass, and metals, and it is considered a hazard waste because it has toxic substances such as heavy metals or brominated flame retardants. However, the shredder life fraction may also contain critical metals, such as precious metals or rare earth elements. And although this fraction has been very little investigated, there is really a need to fully characterize its content in order to determine the potential recovery of valuable materials. So in this study, we want to investigate this shredder life fraction to address the following objectives. First, the study aims to determine a proper sampling protocol to obtain a representative sample from the shredder life fraction, and also to develop an appropriate chemical method to quantify the content of around 15 metals, including base and critical metals. The second objective is to test whether it is possible to observe a significant difference in the content of critical metals in a batch once you remove one component of the vehicle before the shredding step. So with this in mind, the experimental design consists on 2 batches, each of them with 100 vehicles per batch. The first batch will have vehicles with the engine component and the second one without. The sample representation is the key element in this study because of the complexity of the fraction. So we plan to do it as in the following video. Once the shredder life fraction arrives, which is depicted in the orange symbols, it will come into the conveyor belt. Then, every 30 seconds, my colleague Charles will take one bucket of a shredder life fraction. First, he will deploy it in sample 1, and after another 30 seconds, he will take another bucket with a shredder life fraction for sample 2. This process will be repeated systematically until the end of the batch. These 2 samples per batch will go later on through a series of shredding, separation, and subsample steps to obtain samples suitable for chemical analysis, meaning only few grams of sample with a final particle size below 1 millimeter. Since we don't have yet results from this experiment, the final slide presents the literature results from 3 different batches corresponding to 2 different studies, and I can give you an idea about what we are expecting. The graph shows the mass fraction in milligrams per kilogram of a set of 17 metals in a shredder life fraction. So first you can see how the mass fraction of this list of metals disperse up to 6 orders of magnitude different, which is quite a lot. Then, checking closer, you can see how most of the results agree quite good among the different batches. And finally, as an interesting information for today, I want to see the example of, for instance, neodymium with a mass fraction of 30 milligrams per kilogram in the Schroeder life fraction. When we transform this number into the mass of neodymium obtained in a year, and considering that in Switzerland is generated 17,000 tons of Schroeder life fraction per year, it is really interesting to see that we could potentially have 500 kilograms of this metal from the urban mine vehicles. I thank you very much for your attention.
Thank you, Nora.
So it's back to me, I guess, again. Well, there's not much to say from my end at this stage, other than welcoming Sebastien Farnaud, our next presenter. Sebastien is a professor in enterprise and innovation in healthcare and technologies at Coventry University in the UK. And he's going to talk about bioleaching-based processes for the biorecovery of metals from electronic waste. So Sebastien, the floor is yours.
Thank you, Michael. Let me share my presentation. Share. Here it is. Up. Can you see my slide there, Michael? Yep.
Yeah. All good.
Thank you very much. Thank you very much for the for giving me the chance to discuss what we do there. I think I really have to thank the previous speakers because they've done a really great introduction. That's great. Now, more than going through the issues in detail, I just want to remind us there are two major issues. The first of all is that critical material and many of the metal become rarer, so we really need to get them back, to recover them. But I think there's another issue we need to consider, in which method are we going to use to do that? Because the key is that circular economy or not, we need to have method which are sustainable. And this is why somehow the as a group of research that work on the biorecovery, we decided to try to adapt bioleaching to the recovery of metal as a whole, base metal, noble metal, and rare earth. So first of all, the bioleaching, what is it? So briefly, I could talk about it for ages, and I tend to get carried away, so do stop me. But in a nutshell, what is bioleaching? So it's a very, very simple method that helps us to recover, to extract, I would say, metal from a solid support using microorganisms and to bring the metal back in solution. The key is that it's a method which has been used for decades in the mining industry, but as part of in a recovery of material from waste, it doesn't really develop, particularly in industry. I think it is used in academic centers, but very rarely applied into industry. The microorganism we're talking about, the bacteria mainly, with the main one, which is Bacillus for oxidants, and then also some of them which are some fungi. But what is important to say there is that most of microorganisms we use are completely are very easy to find to start with, very easy to grow, and also they're non-toxic, an important point. If I want to briefly describe, there are different kind of bioleaching, but briefly describe the way it works. So I think if you see my my arrow there, my mouse here, so let's say this is your bacteria in the middle. And the bacteria per se, in this case, is a bacteria that needs iron to actually for its own metabolism. So if you do feed this bacteria with some iron, some ferrous iron, it will oxidize it to pick up the electron into ferric iron. That's what it does. Now, because ferric iron is really unhappy in any medium, in turn, it will find somewhere else to pick up an electron, something else to oxidize. So if you grow this bacteria in a medium where you got, for example, a lot of copper, is iron in turn, which has been oxidized by the bacteria, that would oxidize the surrounding metal, in this case, copper. And by oxidizing it, then copper, in a nutshell, gets released in a medium. And by doing that, now iron is back to ferrous iron, which the bacteria in turn will reoxidize. So we've got an endless mechanism, circular mechanism, where you feed your bacteria with iron 2, which is oxidizing iron 3, in turn oxidize the metal around. So you can have an endless cycle where you can, by feeding iron with feeding the bacteria with iron, you can oxidize the surrounding metal. The method is a bit more complicated when it comes to some other metal, but as far as I stand, empirically we can find that by definition, all metal can be oxidized. So there's always a way to apply the technology. So what we did at Coventry, we decided to try to apply this to bring that to industry. And we had a collaborative project, which is going to finish in a couple of weeks, in fact, which was a 3-year project with a cost of around £250,000, funded by Innovate UK and led by the company we're working with called N2S, for Network to Supply, which is an English company that works with the recycle of electronic waste. There were 3 main points. The first thing we wanted to do is to make sure that for this company, we want to create a bioleaching plant at N2S at the premises, which was a bit of a challenge because that company has never heard about anything microbiological. Then from on our point of view, we did have to confirm through a pilot study that we could actually really extract metal from PCBs. And finally, once we got a proof of concept, we really wanted to develop that in efficient methods. So altogether, as a larger point of view for Innovate UK was, first of all, we're going to stop to send things abroad and lose all those metal to other places. But from my point of view, it was really to use a toxic method that would actually have a very high carbon footprint. And also altogether, not to forget that compared to classical method, we wanted to develop methods which are much more efficient than the existing one. And altogether, so this has been going on for quite a while, and the one I chose to demonstrate here is going to be copper, which is the main metal in all these PCBs. So in a nutshell, what you've got, you start with your PCB that you shred, and then you literally feed your bacteria with this metal, with iron also, and you end up altogether having an extremely pure copper foil, which the good thing is that not only can go back to do some other PCBs, but because the degree of purity and selectivity is so strong that you're opening many other supply chains. So altogether, what we intend to do, and that's going to be my last slide, is that in this case, you start with your we, and of course, we have combined a bioleaching-based method with other separation. So in the first instance, for example, you got a noble metal on one hand, you got your strip board on the other side, and then you component there. And what you do is that through different approach in bioleaching, you end up having very pure metals. So I've got a copper and a gold there, but also a representation of cobalt, which is something really, really challenging nowadays, as we know. And what we need to keep in mind there is that, as I said, not only we can go back and reuse this metal within the same supply chain, but altogether, these got to be applied to wrapping, to solar panel, to electric batteries, and so on, which you've already started. And altogether, you can then recycle not only the material to the same supply chain, but open to the others. So altogether, you got a method which is strongly environmentally friendly. You got bacteria you grow at a relatively low temperature, no need for pyrolysis, no need for strong acid. You got something which gives us really, really specific metal, and you got some metal which is highly purified that you can decide to send back to any supply chain. So I think it's really something that has been used in the mining industry for decades, and it's really now time to, we've proven we can really use the methodology in recycling waste. Thank you very much. I'm going to stop sharing. Oh. Thank you, Michael.
Thank you very much, Sebastien. Lorena, back to you.
Yes, back to me. So our last speaker is Ms. Doska Rokavec. She's head of the Mineral Resource Department and project manager at Geological Survey of Slovenia. And she will be exposing her work, Southeast European Mineral Register of Primary Raw Materials.
Yeah, thank you very much.
You.
And good afternoon from Geological Survey of Slovenia in Ljubljana. Sorry, may I now share my own screen? Is it okay or not? You cannot screen. Okay, then okay. Okay, please give me a hand, Mrs. Lorena. I tried to share my own screen of my new presentation, but I didn't succeed.
Farnaud is Just enable
Yes,
yourself
yes.
right now. So you should be able to share right now. your
Okay,
presentation.
super. So I try one more time, or yes, I think it's the right one. Do you see my my screen? Okay, thank you very
Yes,
much.
everything is okay.
So I come from Geological Survey of Slovenia, and what I would like to represent shortly our work in the project, so-called Reserve project, which have been worked in for the past 3 years. The consortium was actually consists of 14 partners from 12 countries. The most important is the participation of task partners from West Balkan. Since European Union strives for its own raw material sources, mineral commodities in EU neighborhood are become of great interest, and West Balkan is recognized as one by European Commission as one of the significant mineral potential. So therefore we engaged National Geological Survey from Serbia, North Macedonia, Bosnia and Herzegovina, Montenegro and Albania. And what was the main aim of this project? To connect this region to Pan-European Mineral Intelligence Network. Now it's called EGDI. It's European Geological Data Infrastructure huge platform, which almost represent all European countries, but we can see here on the map that the region part of Southeast Europe is still not a part of this EGDI system. Therefore, it does mean that their data, mineral data, of course, are still not included in the European mineral intelligence system. And from our project work, we actually succeed to engage these numerous data from West Balkan to become a part of EGDI portal. Here's the screenshot from this portal. All the data are, of course, Inspire aligned. So the creating of this West Balkan Mineral Register is of great importance for this region and also for the whole European Union. The register consists of 2 parts, primary and also secondary raw materials. Primary, of course, counts the primary deposits, mineral deposits, and secondary raw materials means the mine and metallurgic waste sites. So here is the web page site from our so that's our presentation of the whole project, which created this huge register of 6 West Balkan countries. Actually, we include almost 500 primary mineral deposits and almost more than 1,400 mining and metallurgic waste sites covered all over the West Balkan Peninsula, this region. And of course, we made a specific emphasis and highlighted also critical raw materials and mapped actually more than 100 primary mineral deposits, including magnesite, borites, antimony, phosphates, platinum, cobalt, lithium, and some others. Here's on the other side, on the other slide, we can see the sites, number of sites mapped within this 3-year project. So critical raw materials and within also battery minerals. So what is our ambitious plan for the future? In the next period after the project lifetime, we intend to include, to map also also mineral data from the countries that are still represent a lack or a white spot on the European map. And with this action, the European map of all primary and secondary mineral resources and its data will be fulfilled. So that is actually our contribution to the European mineral intelligence network. Thank you very much. That's all from my side, and regards from Ljubljana.
Thank you very much. And we already have some questions for yourself, for all of you. And maybe we can start with a question that is addressed to all 4 of you. The question is,
yes.
The question is, I'm curious about the general view of participants on the development around product passport and how this will affect CRM management through the supply chains. So maybe we could go on the same order, like starting with Ajay, and then could Nora and Sebastien and Duska answer?
Can I go ahead? Can I take the question first,
Yeah.
Lorena?
Okay.
Of course.
Yeah, so thanks for the question, and a very, very interesting direction to orient our discussion now. Yeah, so the product passport would be essentially help in getting many valuation related complexities resolved, because this will also help to create a database of minerals and materials which are used in different products, and the origins of these primary raw materials. So this will eventually help us to count overall feedstock, and based on the composition and the nature of this feedstock, we could then develop requisite technologies and implementation approaches. That would be our take.
Thank you, Ajay. And Nora?
Maybe I can just try to give a brief thought about that. From our type of experiments, one of the key questions that we have is also which kind of components from the car, for instance, can be removed before. So with more further information about what contains each of these components, it will help also to kind of remove it before and probably create a better recycling for precious metals and rare earth metals.
Can I follow up on that then? Yeah, I think it's a very good question because it's really, really essential. It's the only thing that will make the economy a circular economy. As we stand, if on our mechanism, for example, bioleaching, we first need to understand which metal we're dealing with for the process in itself. So one of the issues we have when I talk to a very large, famous company that make a lot of computer, I'm telling them, well, if you tell me what is in your components, that's going to help a lot. But then they tell me, well, we don't know what is in the component because we get that from somebody upstream. And these following the material, this recording to know what is coming and where it's going is going to be so important on developing the right technology, knowing what the material is. Another thing I want to mention is that I was talking recently to an EU consultant about cobalt, and he was telling me, well, your method is fantastic, but the question is there enough cobalt in urban mining to satisfy the need for the demand for the batteries? And the key is that you look for information. We don't have it. We can only estimate how much metal, how much cobalt we think we do have in a different element. So this is the key. If from the start we know what are the material, so what is the method we can apply and how much we're going to get back is fundamental. There won't be any total circular economy if we don't have this traceability and identification of metal. It's as simple as that.
The Duska.
Yes, thank you. Do you hear me? Sorry. Aha, okay, thank you. So my opinion is that the whole value chain should be followed, of course, and also this product, so-called product passport, is might be crucial, and it's important to be supported. But otherwise, I'm actually not the expert for the whole circular economy. Just the beginning, just the initial or primary part that is exploring and discoveries of new primary raw materials. But of course, we all aware, and we have to aware that the extraction, first of all, exploration and then extraction and mining of raw materials should be in a green way, let's say so. But it's easier to say than to put it in a reality, since the materials from the sites where the labor force and every nature is ruined and everything's going wrong, since those materials will be much cheaper on the market, then we could not reach to the final and wished conclusion. And thank you very much.
Thank you.
Can I add something?
Yeah.
Exactly on this. Just to add that for us was actually is even part of our motivation to create such a big experiment, because we realized that for the vehicles, there is no detailed information about which contains all of the different components of a vehicle. Not now, and even less of the new vehicles that are coming to the market. So for us was to come, let's say, from the back part, to try to analyze all of the different fractions that are coming to really determine at what concentrations precious and rare earth metals are in vehicles, in order to understand how to later on improve the recycling system. So of course it will help a lot.
Can I maybe just, there was another question in this context asked about sort of this product passports and product stewardship traceability in the context of critical raw materials management. The feasibility is an open question to me, asked that person. Any experience you could refer to? So any schemes or any, well, at least trials that you are aware of where that traceability and product passports actually worked? I don't know, Sebastian or Ajay, yeah. You raised your hand.
Sebastian, go ahead, Sebastian. I can go.
Just a quick example. I was at a trade event a couple of weeks ago, where, because we're where we are, the material being used, there's so many different, the supply chains are multiple, and many users, and we end up with a product. And the problem is that, that's what you're emphasizing there. Where do we start? Do we start from the one who make it and tell us, okay, that's where you go, or do we start from the end? And I was talking that I've talked to different angle, and the one I was talking to were at the recycling level, people are trying to create this monitoring that you can analyze whatever you end up with, and then following it on to see where it's going next. And I think if we start to maybe it's going to be working at all different levels, because this is started working quite well. So you end up with a product, you end up with some waste, and you decide wherever it's going to go next. And then you got other people making whatever their components or car parts or whatever, and having some analysis at level and see whatever they're dealing with. On both angles, it will work pretty well, because at some stage we need that kind of patchwork to work. One of the issues I had was, again, talking to one of those largest producer, telling us, well, the problem we've got is that if we start to ask our manufacturers to have some sort of code on their components to tell us what are the mineral in there, the problem is that we can't do that because of some the competitive market. The problem is that we tried to go to the producer and tell us, can you just put a little barcode on your component to see what in there? They refuse to do it, because in fact because of competition on the aspect. So I think what we're going to face at some stage is there's some people trying to face and trace whatever mineral they got, but there's some origin from the start. There's such a strong competition that people don't really want to say what is in their product, and it's a bit of an issue. So I think we need to be aware of all the different aspects. How are we going to do that? And that's, I think, it's a bigger issue than it seems.
Ajay, do you want to follow up as well?
Yes, so I could share an example of a success story about such development of database and controlling feedstock. Actually, it is from lighting industry, also one of the prime feedstock we are processing. After the implementation of Minamata Convention, which was for mercury-based raw materials which are toxic. So the effective legislation has been implemented, which is keeping track of this feedstock. And this is nothing but a concept of a product passport, that from beginning to the end, such a value chain or such a material feedstock could be monitored. And it has been successfully implemented in lighting industry. So that similar approach could be taken up by other electronics industries as well, without having fear of competition.
Thank you very much, Ajay. We have another question for both of you, to Ajay and Christian. What role can electronics producer play to help scale up the emerging recovery technology for critical raw materials?
Yeah, so I also answered this question in chat. So there are two ways also for the other panelists to let them know. So there are two ways how electronics producer can help. One is that establishing the database, like similar to product passport, what we are discussing right now, and track the materials which are used in the products. Of course, within the lines that confidentiality has been, let's say, respected. And what the least they could offer without having fear of confidentiality is to establish their own reverse supply chain. Then the materials and feedstocks are accessible at their own system. They can use the component if it is possible, and they could give in a destructed format for the recovery of other primary raw materials or recycling of other primary raw materials. And then the second way is that trying to use a recycled material, because usually the circular economic or recycling solutions they have to end of the day compete with the mineral resources in pricing, because even if we are promoting circular economy, there is no incentive or, let's say, leverage that we can get in the front end market. So initially it would be difficult for electronics industry that they could prefer recycled material over the primary mined material, which is cheap with some material to the throwaway prices. But at least they could start with hybrid model, that they could use the partial recycled material without affecting their own economics, and this will eventually help catalyze the recycling industry of critical raw materials. This is how the electronics industry can help.
Okay, thank you, Ajay. We have two other questions and just 4 minutes left. maybe we could end with 1 minute per each one, so you could give us your final thoughts. And thank you very much, but we lack of more time to really end all the questions we have. Remember to go on WOVA and vote for the best presenter and best work. You will have the ID numbers of each presentation and speaker, so you could vote over WOVA, please. So final thoughts, each one. We have just 4 or 5 minutes left.
So I just spoke. Do you want me to continue? Yeah. So just to close session, it was indeed a pleasure to join this esteemed panel today, and to understand the constraints, let's say in primary raw material circular economy, as well as I was happy to see that the value chain is being extended to the cars, and there are alternative approaches like bioleaching. Means optionality is actually the key in the recycling and circular economy, because it increases our chances of success as a society. And yeah, we are happy to keep this discussion ongoing, and also the efforts. Over to you, Nora. Thanks.
Yeah, thank you very much also for giving us the opportunity to present here. And just after this small session, I can see that I am very curious to know more about the work of Sebastien and Ajay, because are in the same line of our research. So this is a really perfect platform to keep discussing and learning from each other. So thank you.
So just a quick word. It's fantastic to several things to see there's such a, it is happening. There's a lot of people from all over the world, and we're sharing the same ideas, and it's there. So the big issues are, like we say, we got material are disappearing. They're rare. We really need to do something about it. Waste is becoming a major source. But then the problem is that, and we highlighted slowly to it, business, it has to be interesting for the business. So this is a critical thing. So we need to look at material need to be recovered. It has to be in a sustainable way, but it has to be interesting for businesses. And they can't be separated, those guys. And this is why it's really good to work together. You can see some of you are, we are purely academic, but we work with companies. Some of you are institute that also work with a spin-off and so on. I think it's fundamental. It's only working together that we could do this circular economy, which most of the time is not. I can see the problem in terminology for me is that we got those big, if you look, you go on Google, you look for picture for circular economy, and a big cycle like this, but what happens is that you start and it ends, and it doesn't go anywhere else. The key is that we need to start from the end. We need to have the recovery, talking with the manufacturers, with the dealers, with the designer, so that we can have this actual circular economy that we're talking about. When, for example, when Nora, you talk about those car bits, you're right. The point is that first you need to know what is in there. When those guys build the car, they need to talk to you, and not just to the customer. And this is exactly where we need to be working together with the manufacturers, not just with the waste guy. No, we waste guy talk to the designer. This is the important thing. Thank you very much.
Thank you. Final thoughts, Daska?
You're muted.
So I'm also grateful to had the opportunity to participate today's event because I think that the communication, discussion between different experts are essential, and to share the knowledge and experience is at least part of the success on the common path to the end goal. Thank you very much.
Thank you all. We had 32 participants today, and remember to vote, please.
Yeah, maybe Farnaud, you can bring up that one slide again as a final reminder, showing the participants with their presentations today. So please vote on those presentations and give all the 4 presenters we had today a chance to actually win the big prize on Thursday. With that said, that brings us to the end of today's session. Thank you very much for joining us, listening to us, and also participating in the discussions. It is much appreciated. And with that said, have a great rest of your day and enjoy the rest of today's sessions as well as tomorrow's and Thursday's session. Thank you very much.
Thank you
and
very
see
much.
you soon. Bye-bye.
Thank you very
Bye-bye.
much. Bye, everybody. Thank you.
Thank you. Have a nice afternoon.
Thank you.